Okay, we will do 3 examples of mean hypothesis tests, and then we will be done with Chapter 8. So here we go. A data set about speed dating includes like ratings of male dates by the female dates. The summary statistics are n equals 196. The average like was 6.56. I don't know, maybe that's out of 10. Standard deviation 1.89. Notice it's S, so that's our sample standard deviation. Use a 0.05 significance level to test the claim that the population mean of such ratings is less than 7. Well, just right off the bat, we see that our sample was less than 7, so this must be some pretty strict ratings, or maybe the guys weren't so great, I don't know. So we notice that we're less than 7, we're 6.56, but it's pretty high standard deviation, 1.89. So maybe it's possible we could have gotten that by chance, or maybe it certainly is that the ratings were less than 7. That's what this test will help us solve. So, game is always the same. What's the null hypothesis? Alternate hypothesis. The null hypothesis is that our mu this time is going to be equal to 7. Notice it's not p and it's not standard deviation, but it's a mean we're looking at here. So that's supposed to be mu, but there we go. So it's mu is equal to 7 will be our null hypothesis. And the alternate hypothesis, we're testing, our default is a not equal to. But it says here we're testing the claim that such ratings is less than 7. So that means our alternate hypothesis is that we are less than 7. Okay, before we do the test statistic, let's find the critical value. This is the value we have to defeat in order to reject the null hypothesis. Now, let's find the formula for the test statistic. So we grab our trusty dusty cheat sheet. Okay, we are conducting a hypothesis test, and we are indeed testing a claim. So we come down this branch, we only have one sample, and we're testing it to a claim. This time it's not a proportion, so we ignore 8.2. It is indeed a mean. Now, you see that we have 2 branches here. Either mu is unknown, sigma is unknown, or sigma is known. So here is the idea, okay? Sigma is the population standard deviation. And most of the time in real life, we don't know it. And so as a result, we're going to use this formula right here, and I'm going to put an 8.3 by it. This is perhaps the most common formula on the entire page. It's when we're testing something with a mean and we don't know the population standard deviation. I'm just going to leave it at that. This is the most common test. So notice that it's t equals. If we do know sigma, then it becomes a z equals. But since we don't know sigma, it's a t equals. So let's write it down. T equals x bar minus mu divided by s divided by the square root of n. Okay, there's our formula. So that means that to find our critical value, we need to use a t-table. Now, the homework doesn't ask us to do this, but I just want to get a full understanding of what's going on. So we know that we need to find a t critical value, and to do that, we need degrees of freedom. Remember that degrees of freedom is almost always n minus 1, and so in this case, our degrees of freedom, we have 196 cases, so degrees of freedom is going to be 195. So 196 minus 1. So what I'm going to do now is we are going to pull up our t-table, which I already have, which don't forget, that is available on D2L. Now, we scroll down. What was our confidence level, and was it 1 tail or 2 tails? Well, because of this less than sign right here, it's a 1 tail test. And our confidence level was 0.05. So 0.05, you can, up at the top, you have the alphas. It's a little bit harder, so 1 tail, 0.05 would be the same as a 95% confidence 1 tail. Okay, so in any case, 0.05, 1 tail. So up here is alpha, down here is the confidence level. Okay, so use either one. So alpha 0.05, 1 tail is this column, and we had 195 degrees of freedom. So the closest value to that is 100. So 1.66 is our critical value. 1.66. That's the number we need to beat to reject the null hypothesis with this formula right here. Okay, so let's figure out our numbers. This is actually easier than the proportion one, I think. X bar is 6.56. Mu is 7. Our standard deviation was 1.89, and our sample size n was 196. That's it. Now we grab the calculator. Be very careful here. I'm going to put it all in at once, but only do this if you're really careful and know what you're doing. I'm going to start by doing a parenthesis and doing 6.56 minus, sorry, there's a glare, 6.56 minus 7. Okay, that's the entire numerator, 6.56 minus 7. In fact, let me write it out for you. It's going to be t equals 6.56 minus 7 all over the standard deviation, 1.89, divided by the square root of n, which is 196. So that's what it looks like with all the numbers plugged in. So 6.56 minus 7 divided by, I'm going to do another parenthesis, 1.89 divided by the square root of 196. I'm going to go outside of the square root and close the parenthesis. So notice how I was just very careful to put the entire numerator divided by the entire denominator. I press enter and I get a test statistic of 3.259, which is the correct answer. So the test statistic is, if you round to where the book wants you to round it to, they wanted it to round to 2 decimal places, so that's negative 3.26. You do include the negative sign. Remember, if it's a left tail test like this, if it's a less than left tail, you will have a negative test statistic. That's okay. That's why we take the absolute value of it when we compare it to the critical value. And you can see that here we're going to reject because 3.26 as a positive is bigger than 1.66. So we're going to end up rejecting the null hypothesis before we even see what the p is. Okay? So when we see the p value, which we'll do right now, we know that it's going to have to be smaller than 0.05. The p value has to be smaller than alpha because we know we're going to reject because this t statistic, absolute value, is bigger than the critical value. Okay, let's actually find the p value, and to do that, we need technology. And so if you come back to D2L, you'll notice that I have for section 8.3 and 9.3, I have a t-test calculator. So let's click that. Boom, here we go. So this is a little bit limited, but that's okay. In this case, our alpha level was 0.05. The degrees of freedom I need to type in. Remember that the degrees of freedom over on our notes was 195. So the degrees of freedom, is 195. T-score, that is our test statistic. And I'm going to go ahead and put in a couple extra values, negative 3.259. That should be enough. Negative 3.259. 5% one tail because we were less than. And that's it. Check it out. It says that the p-value is 0.00066, which is the correct answer. So the result is significant at p is less than 0.05 as we predicted. We said that this number had to be smaller than 0.05 because we had already found that out from the critical value. So 0.00066. The computer wants us in our homework to round in this problem to 3 decimal places. So we could write 0.001, which is the answer the computer was looking for. It'll tell you how many to round to. So test statistic absolute value larger than critical value means that the p-value is smaller than alpha. It always goes that way, and I got it right here. Test statistic absolute value larger than critical value means p-value less than alpha. Reject the null hypothesis. There is evidence to conclude that sufficient evidence to conclude that the mean of the ratings was less than 7. We accept the alternate hypothesis. So sorry guys, your average rating was smaller than 7. Better luck next time. Okay, 2 more examples to go. If you feel like you're already ready, go for the homework. But if you want to see 2 more examples, I will make those videos for you next.